We're going to derive the governing partial differential equation called the heat diffusion equation. In 2D. Okay. We've done this little game before in thermal and fluids. We take a small element, a differential element. In this case, we'll consider it to be a solid, and we're going to look at all the energy terms coming in and going out of that solid. A differential element means it's dx by dy. It's going to be 2D. We're going to ignore the z right now. So here's our little control volume. It's a differential element. E dot G is the energy generated internally. E dot storage is the change in stored energy. Now this is conduction. The energy coming in on the left-hand face comes in by conduction. We call it Qx. We assume it varies continuously. We write the energy going out as Qx plus dx. Energy coming in the bottom, the face down here, Qy by conduction. Energy going out the top by conduction, Qy plus dy. Okay, so with that, we can go ahead and start putting some terms in there. I think what I'll do, yeah, let's put in, let's put Qx in here. Qx is conduction, so it's minus K A dt dx. The area through which the heat's conducted is this piece of paper. Its height is dy. Its length in the blackboard, we'll say 1. So dz is 1. So it's 1 times dy. Qx plus dx is equal to Qx plus the partial with respect to x of Qx times the distance you move in the x direction, which is dx. Similarly, conduction in the y direction, Qy, K A dt dy. In this case, the area is dx by 1. And expanding that in a Taylor series and neglecting higher order terms, Qy plus dy is Qy plus the partial with respect to y of Qy times dy. The area for the bottom is the paper, so the heat comes in the bottom. This length is dx, so the area is dx times 1, right there. Okay, now let's do the E dot gen. E dot gen, we bring a new term in. It's Q dot times the volume. Okay, and the volume of that little differential element is dx times dy times 1. So now we have a new Q term. It's Q dot. That Q dot is energy generation per unit volume. Per unit volume. So over here, here's our Q's now. Q all by itself. Q prime. Q double prime. Q dot. They're all different, but they're all Q's. The first one, watts. The second one, watts per meter. The third one, watts per square meter. Heat flux. And now we got the fourth one, watts per cubic meter. Okay. So 4 different possible Qs. Know what each one means. If a problem asks you on homework or exam for the heat flux, you know what they're asking for. If they ask you for the heat rate, you know what they're asking for. Q dot, you know what they mean. Volumetric energy generation. And the last one is the storage. I'll put that up here. E dot storage, mass, Cp, dt, d time. The mass of that differential element is rho times the volume. dt, d time. So this is equal to the volume, dx by dy, times 1. So rho dx dy partial t with respect to time. Okay, now we put those in the energy balance equation. Okay, energy balance equation. It says what comes in minus what goes out plus the generation equals the change in stored energy. Look at the picture. What comes in by conduction? Qx plus Qy. What goes out? Okay, look at the picture, or this equation right here. And then we have Qy going out. Okay, and then we have plus E dot gen down here. And then we have that equals Q dot storage up here. Q dot x minus Q dot x cancels out. Q dot y minus Q dot y cancels out. We're left with partial with respect to x of qx. There it is. Okay. There's a minus sign in front of there. Minus k dy. And we have dy partial t with respect to x times our dx. And then for the second term, the y term, it's minus partial with respect to y of qy. There it is. Minus k dx partial t with respect to y multiplied by dy. Okay, and that we have our E dot gen, which right here, E dot gen plus Q dot dx dy equal E dot storage right there. And lucky for us, we see each term has a dx dy in it. It comes outside the partial. Dx dy, dx dy, dx dy, dx dy. That's how we derive these differential equations. Minus sign, plus sign. So partial with respect to x of k dt dx plus partial with respect to y k dt dy plus q dot is equal to, there should be a rho CP here for storage. I had it over here. Oh, here. Yeah. Oop, there should be a rho, pardon me. Rho CP up here. Rho CP. Okay, rho CP. Partial t with respect to time. We're going to make an assumption here to make life a little easier right now. We're going to assume the properties are constant. Assume constant properties. The k value then comes outside the partial sign. K comes outside the partial sign. Divide through by k. Okay, so we have second partial t with respect to x, second partial t with respect to y, plus q dot over k is equal to rho cp over k partial t with respect to time. But rho cp over k is just what we defined back in early chapter 2 as alpha, the thermal diffusivity. So the right-hand side can be written as 1 over alpha partial t with respect to time. This boxed equation is called the heat diffusion equation in 2 dimensions. The heat diffusion equation in 2 dimensions. If it's 3 dimensions, all we do on the left-hand side is add the second partial of t with respect to z. And that equation is in the textbook 222. Yeah, 222. Equation 222. If you want it in cylindrical, coordinates, then look at equation in the textbook. We're not going to derive it. The equation in the textbook is 226. If it's in spherical coordinates, equation 229. Okay, so there's the governing partial differential equation. What's the purpose of that guy? The purpose is to solve it where you get the temperature as a function of the variables. So you solve to get temperature as a function of the variable x, the variable y, and time. In chapter 3, we'll solve a very, very simple version of that with a lot of assumptions. But for right now, that's the general form. What are the assumptions in the boxed equation? Okay. There it is right there. There it is. But you can't solve a PDE, or any DE, unless you give somebody boundary and initial conditions. So we need boundary and initial conditions to solve this. So we'll do the initial condition first. At T, the simplest one is the initial temperature. At T equals 0, the temperature equal Ti, where the I, of course, stands for initial. For instance, if I had a 3-inch by 3-inch cube of copper, and I heat it up to 100 degrees Fahrenheit, and then I blow colder air over it at 50 degrees Fahrenheit. To solve that equation in 3 dimensions, then, what I would need is an initial condition. So my initial condition, called IC, is when time equals 0, the temperature anywhere in the cube is 100 degrees Fahrenheit. Okay, that's it. Now I need a boundary condition. Okay, we're going to make it easy for ourselves now. Let's say it's one-dimensional. Okay, one-dimensional. So all we need is one condition on that. So boundary condition, there'll be 2 of them. Number 1, only with x. Boundary, I'll put in there. Boundary condition 1 and boundary condition 2. We need these. Somebody has to tell you what are the boundary conditions. Okay, let's put some down here. Typical boundary conditions. Okay, these are on table 2.2. Yeah, table 2.2. Okay, type 1. Type 1 says constant surface temperature. These aren't all of them. These are just typical ones, the ones we use the most. Constant surface temperature. So if we have a surface, and here's the material, thermal conductivity K, we're measuring X from the surface into the material, and somebody says, oh, by the way, I'm going to keep this temperature at the surface at X equals 0, equal constant surface temperature. Then temperature at X equals 0 for any time t, for any time, is going to be a constant value Ts. Okay. You could probably treat that wall right here as a constant temperature wall. I guarantee you the outside wall is hotter than the inside wall right here. So if I'm going to analyze this wall by conduction here, the wall outside, especially in the afternoon when the sun hits that wall, the outside temperature is warmer than the inside wall. And what's my boundary condition? Well, it could be convection, but I would probably assume maybe to start with that temperature is going to be constant. I don't think it's going to vary with time for the next half hour. I don't think it's going to vary with X and Y very much from the middle of the wall to where my hand is. I think the temperature is pretty constant there. So I might model that as a constant temperature boundary condition. Number 2, constant surface heat flux. Okay, for this boundary condition, here's a wall again. Thermal conductivity K. I'm going to measure X into the wall. X equals 0 is the surface. And for this one, I have a constant heat flux on that wall. QS double prime equal constant. Okay? So a surface energy balance at the wall tells me the heat provided by the constant heat flux at the wall must go into the wall by conduction. Okay? So minus K dt dx equal, that's the heat flux, QS double prime. And this dt dx has to be at, of course, the surface, X equal 0. Constant wall heat flux. Number 3, perfectly insulated. adiabatic. The proper word is adiabatic. Adiabatic means the heat flux is 0. When someone says insulated, you always don't know if it's adiabatic or not. Okay. Homework get over here, Ari? Homework going on? Thanks, okay. If you came in later, here's today's homework up here. Okay. Adiabatic. This guy is 0. No heat comes in or goes out. 0. QS double prime equals 0. Which means that minus K dt dx has to be 0. Which implies that partial of t with respect to x at x equals 0 must be 0. Okay, that's the one you want. Partial t with respect to x, 0. 4. Convection at the boundary. Okay? Here's a picture. X. Now we have convection. T infinity. H on the surface. Surface energy balance says the energy that comes in by convection must go out by conduction into the body. So here's our equation. It's more complicated. It has a temperature on both sides of the equation. dt dx at x equals 0 and the temperature at x equals 0. It's a more complicated boundary condition. So, you've got the governing differential equation, and then you've got the correct boundary conditions. Once you apply those to the differential equation, you get a solution for temperature in the body as a function of x, y, and time, if it's two-dimensional. I told you about this constant surface temperature. You know, when steam condenses in a condenser, in a power plant, when steam condenses in a condenser at the condenser pressure, you've had thermal, you probably know this. It condenses at the saturation temperature of the pressure in the condenser. So the tubes are like this in the condenser. They're carrying cold seawater, probably Pacific Ocean. The steam comes in here, it condenses into droplets at what temperature? The temperature, saturation temperature for the pressure in there, and then of course the droplets combine and they go off into the condenser hot well. Every time they condense, that temperature is the same. It's a saturation temperature. Yeah, okay. That's this guy. Constant surface heat flux. Oh, you could buy electric type heating blanket, industrial type blanket, and slap it on a wall, and then hook it up to a voltage supply, and provide so many watts per square meter from your electrical conducting blanket on there. Sometimes these solar power plants, especially the one up at 395 and whatever, it's Highway 58 on the way to Mammoth, for instance, you'll see it on the west side. Big parabolic trough collectors. Some of those collectors carry heat transfer oil in the pipes that go through the focal point. And at night, they don't run the collectors at night, of course. At night, there's oil in there. Or you could put the oil back into a big storage reservoir, or leave the oil in the pipes, and the pipes are wrapped with the electric heating blanket. And they trickle a little bit of power through it, or a little current through it, just enough to keep the oil warm, because when you throw in the morning, when you throw that pump switch on, you don't want cold oil, very viscous. Your pump might burn out. So you heat the oil up a little bit so that when you throw that pump switch, the oil is less viscous. So you wrap it in a blanket like that again, okay? We all know about adiabatic, you know. You put enough insulation on, it's going to be pretty much adiabatic. You've heard the term adiabatic turbine. Oh, you know, guess what that means. You know what that means about the turbine, yeah. From thermal. Convection on the surface, everything we do on the surface of the earth here is about convection. On my body, on this front wall, on the outside wall, on the tree trunks, on the street, the asphalt, that's all convection. So there's a lot of convection going on. Okay, so anyway, and there's more. Obviously, we're building some kind of space vehicle. We can't, there's no conduction, there's no convection, it's all radiation. I don't have radiation up here because that's for the advanced group, okay? Radiation's a tough boundary condition, the fourth order in temperature. So no, we won't be considering radiation on this list, although in the real world, yes, it does happen frequently. Okay, so these four are the only four you're going to be responsible for in our heat transfer course. Okay, so now we have that set up. The heat diffusion equation with the correct boundary conditions. Okay, let's look at some problems to see how we use all this material in Chapter 2. We're going to start off with a very early problem. You'd think problem 2.1 would be the easiest problem in the whole homework set at the end of the chapter. Not true, not true. So problem 2.1 is very similar to your homework problems 2.2 and 2.3. So I'm going to go through 2.1 to give you some major hints how to work that. Let me read it first. 2.1. There's a picture given in the textbook. Okay, it says we have heat conduction through an axisymmetric shape shown. So it looks like this. We're measuring x from the left-hand side. This is x equal L. He tells me the temperature on the left-hand side is a constant temperature at that surface, and the temperature over here on the right-hand side is a constant temperature on that surface, given constant surface temperatures. He doesn't tell me he should, and I would definitely do that on a problem, that the sides of this are adiabatic, perfectly insulated. Let's see what else we're given here. He says, assume, the problem says this, assume SS steady state. Assume one-dimensional, heat's only transferred in the x direction. Assume constant properties. Assume no internal generation. Okay. And then he says, sketch the temperature distribution on Tx coordinates. So he wants you to T1, he tells me, by the way, that T1 is greater than T2. So I know T1's a hot side, T2 is a cold side. T1, and then L0, T2. Okay, sketch the temperature profile. Well, you might be tempted to say, oh, I just think it's a straight line. Why shouldn't it be a straight line? Okay, that's one possibility. Then you might say, well, you know, it could be a little bit of curve to it, so I don't know, maybe it looks something like this. Or maybe it'll look something like that. Those are all possible shapes. Well, okay. The problem is conduction, heat transfer. So we're going to write, let's just do something first to make it simpler. Let's do energy balance. E dot in minus E dot out plus E dot gen equal E dot storage. Now, he said that Q dot 0, okay, goodbye. He said steady state, goodbye. Conclusion, E dot that comes in the left-hand face must equal E dot that goes out the right-hand face. If I have 50 watts coming in the hot side, 50 watts has to go out the cold side. Where else can it go? The side walls are adiabatic, perfectly insulated. There's no generation. It's steady state. That's what the energy balance tells me. So right away now, I know what that means. That means that Q in watts equal a constant. Constant. Okay. Let's then write down conduction, Fourier's law. Minus K A dt dx. Q is, I just showed you, constant. Problem said, assume constant properties. Constant. It says then, conclusion, that this thing right here must then be a constant. A dt dx equal minus Q over K. That's a constant. What does the area do as x increases? You can see the area gets bigger and bigger. So the area gets bigger. If you multiply this bigger number by another number, get a constant, this guy better be getting smaller. Otherwise, it wouldn't stay constant. What does that mean? That means as x increases, the slope dt dx must be getting smaller. Slope is here. At this location, same slope. That's not working. It's not that one. Slope didn't change at all. Don't forget a steep slope. Steep slope, shallow slope. Okay, here's a slope here. Okay, go down here. Ooh, big, 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 big. Small slope. Big slope. No, you got it, that one. Big slope. Small slope. Yep, that's it, that's it. No numbers. Sometimes these problems drive people crazy. They say, please give me numbers on an exam. Don't give me symbols. I hate symbols on exams. I want numbers. I know, but sometimes, sometimes this helps you develop engineering intuition. That's the important point. It helps you to draw something without ever having to solve the governing partial differential equation. Okay? That's the key. All right, so that's how we prove that guy. It's that one right there. Okay. If you want to look at Q double prime, Q over A, what happens here? This guy, numerator, is constant. Denominator, as x gets bigger, the area gets bigger. Conclusion, Q double prime gets smaller. That's kind of intuitive. If I've got 50 watts here divided by a small area, and 50 watts here divided by a big area, Yeah, Q double prime gets smaller as X increases. Q, though, 50 watts in here, 50 watts crosses here, 50 watts crosses here. It stays constant. Q stays constant. Q double prime gets smaller, and the slope, dt dx, gets smaller. A lot of stories in there. So your two problems are very similar. The problem 2, 2, 2 looks something like this. I think it looks, yeah, it looks like this. Compared to that guy, okay, so 2, 2 and 2, 3 are very similar. Use my solution as a guide for you. All right, now let's talk about the homework that I passed back so you know what's going on with the homework. All right, let's see. This is what was passed back. This is what's due today. That's what's due next Wednesday. Okay. So on the homework, you can either get a check minus 0, or an asterisk. And if you had me for fluids 311, you know how I do this, so it's not any news to you, but we'll go over it. I'm going to pick up 12 homework sets. I'm going to have 12 grades in my grade book. I'm going to knock out the 2 lowest grades and keep the top 10 homework scores. Each homework set, you can get one of those 4 scores in the upper right-hand corner by your name, typically. You'll see the symbol. If I assign 8 problems and I grade 1 or 2, let's say I grade 1. I graded 1 this time, the first problem, just look at it. You get a check. Okay. If I pick up a homework set with 10 problems and I grade 2 of them, and you got them both pretty much all right, you get a check. If you worked 1 and got it all right, and worked 1 and didn't get it right, something was wrong, or the wrong equation, or the dimensions were messed up, then it'd be a check minus. If I pick up 10 homework problems and I grade 2, and guess what? The problems I grade are the problems you didn't work. Out of the whole set, you worked 8 problems out of 10, and guess what I do? I grade the 2 problems you didn't work. You know, Murphy's Law. Oh my gosh. The 0 means you didn't work the problems I graded, but you worked a lot of the rest of the problems okay. I kind of look and see if you've done the rest of the problems. So that's what the 0 means, okay. This guy counts 1 point. This guy counts a half a point. This guy counts 0 points. The asterisk means nothing was turned in, okay? This is 0 points. Avoid the asterisks, okay? That tells me that you didn't think my homework was worth working, okay? And my ego gets crushed, so it really makes me a bad day, you know. So avoid those little asterisks because they can come back to haunt you. If you're sitting there, I'll be real generous and say you're at 89.4. 89.4. It's like, gosh, by the book, if I round it off, that's an 89, and by the book, that's a B+. Could it be an A minus? Gosh, within 0.6 of a point? One thing I'll do is I'll check the exams and say, well, the first exam, not too good. I don't think he knew how I pick up exams yet. But the second exam was better, and the final was even better. So it's some improvement. So I'll take that into account. And then I'll say, let me check the computer problems. I assigned 2 of them. Oh, okay. Out of a total of 5 points, this person got 4. Okay, decent. Try each one. And then I'll check the homework. And if, I see 10 homework sets, I'll see 6 asterisks. Must have been a busy person. Must have been carrying 22 units because he had no time for my homework. I don't know. Should I go up with the B? Should I keep it there or should I reduce it down? I don't know. Homework's important, so I don't like to see too many asterisks. Okay. I'll tell you, it helps you to do the homework, as you know, when you're studying for the final. All right, on the homework, at the top of the page, yeah, your name, of course. So you've got your name. Then you've got ME 41502. Then you've got homework set number 1. Okay. The reason why I like to see that 02 there is because I'm grading section 1 and section 2. And I've got 34 and 34, 68 people. And I'm grading 2 homework sets. I've got 130 something problems to grade. Anything you do to make my life easier while I'm grading will help you, I guarantee you. It'll make me happier, okay? So if I happen to mess up these problems somehow, I think, oh no. Where's Gina? Is she in section 1 or 2? Where's this go? Well, you know, I check my grade book, of course, but it's easier if you do that for me. Okay, so that helps me. Number 2, this helps both you and me. Near the end of the quarter, the 9th week, you say, gosh, I'm kind of worried about my grade in this class. So you come and see me and say, Professor Biddle, what do you have down for my homework score? And I say, well, I've got down 6 out of 10. And then you say, well, you know what? I've got 7 out of 10. I said, oh, really? I said, well, I've got a 0 on homework set number 3. Well, if you mark these things like 1, 2, 3, and 4, it'll be easy to find 3. If you say nothing, or maybe problem so-and-so and so-and-so, I'll say, I don't know, were those problems in set 3 or 4 or 5? So it's easy for me and you, when we talk about your homework grade, if something's wrong, you don't agree with my homework grade, we'll check every set and see which one is missing and why it's missing. So that helps both of us. So now if you do a problem, let's take a problem, easy one. Q equal, let's just do K, let's do Q double prime, K delta T over L. So K is 1 watt per square, watt meter K. L is a half of a meter. And delta T is 20 degrees C minus 10 degrees C equal 2 times 10, 20. If you don't like degree K, take your eraser. That's from the back of the book. 1 watt per meter degree K in the appendix. Take your eraser and make that a degree C. We said before, that's legal. Cancel, cancel. Watts per square meter. So when I look at the problem, I'll see, did you put down the version with just symbols, the symbolic version? Did you put the numerical values in? Did you put the units in? And did you get the right units when you were done? Okay, those 3 things. Symbolic equation, the numbers, the units, and the answer. On the answer, most people will do that, box it in. Some people will do this, double underline it. Some people have all different ways of doing it. I don't care. They'll put a big fat red arrow or something by it. I don't care. But just somehow make the final answer stand out. And that helps. And the last thing I think I commented on your papers was it really, by the way, engineering green's fine. Do it one side only. It's easy when I'm grading not to worry about what's on side 2. Makes my life easier, one side only. White line paper's fine. I'm not going to tear this up, I'll just show them. What you don't want to do is tear out spiral bound paper and it looks like Velcro, sticking together. So don't do that. But paper like there, white line's fine. Staple, of course, we're engineers, we're not art majors. Staple, yeah. We tell our freshmen, I've told my freshman class, listen, you guys engineers, 90% of our engineering seniors use engineering green. Okay, I tell these freshmen this story. I said, now when you do your homework, this is what you don't want to do. You might have been taught in high school, but change it. You take I'm going to turn my homework in, so I'll fold it, and then I'm going to tear it here, and I'm going to tear it here, and I'm going to fold this little tab down. Am I creative? Fold the little tab down, and I don't have to buy a stapler. Oh, I know stapler only costs $2.95 for a little Cub stapler that big, but I'm going to save $2.95 for gasoline. No, don't do it. It's not worth it for 4, 5, 6 years of your education here. Don't do it. Buy a stapler. So that's what I mean by that, okay? I know you guys don't do that. But freshmen really do, honest to goodness. Okay, the last thing is, if there's multiple problems on one page, it really helps. If you put lines between the problems, okay, it helps me locate the right problem to grade quickly. And the reason, when I'm grading 150 problems, I got to move fast. I can't dwell too long. This helps me grade your homework. And when you're studying for the final exam, boy, is there a big time payback. Because you've got everything organized, ready to go the week before finals, the 10th week, to look at your homework. Plus, of course, you know the story. Keep your homework for every class, because when you graduate, you might need it for your job, especially for some companies who require you to be professionally registered. Aerospace companies, any company that builds bridges or anything where the public is at risk. Oh yeah, they want a registered engineer to sign those documents off. And so if you're going to try and pass the FE exam or the PE exam for mechanical engineering, it's great to have your homework in a little folder to review it. Oh yeah, it sure beats going out and trying to buy a textbook that has word problems. So keep all that stuff, and it'll really give you some payback if you do have to get registered professionally. Okay, now let's go back to homework and look at one more. Let's take problem 31. You have problem 30 for homework, so I'm going to do 31. I think I'll start in the middle. I think we'll be okay. Was there any question on the homework format and the grading and so on and so forth? Okay. All right, let's see here. There's no picture in the book, so there's just words, and I'll read it. Okay, so this is 231. We have a wall. And the wall is 3/10 meters in thickness. And that's L. Let me read it so I can. The temperature distribution across a wall at a certain instant of time. He tells us this. He tells us the temperature across the wall as a function of x is 200 minus 200x plus 30x squared. Okay. Okay, we've got storage in there, so this is a time varying problem. We've got conduction coming in. Okay. K of the wall is given as 1. Okay. That's all right. Now we need. Okay, let's see. Okay, determine the rate of heat transfer into and out of the wall. So part A. Find Q double prime in and Q double prime out. And then find the rate of change of energy storage. So E dot storage per unit wall area. Now, why do I use Q double prime? Because he didn't tell me how big the area was. I know how thick it is, 3/10 meter, but I don't know how big the wall is. So any problem where you don't know how big the wall is, you probably should base everything on a per square meter of wall area. That's why I use Q double prime. Okay, let's find the conduction. Q in minus K, I'm going to do double prime, K dt dx at x equals 0. Okay. dt dx goes out minus 200 plus 60x. Okay. K is 1. Dt dx at x equals 0 minus 200. 200 watts per square meter. 200. Okay. Q double prime out. All right, K minus 1. dt dx at x equals 0.3. 0.3. That is 182. Part B, energy balance. On the wall. What comes in the left-hand side minus what goes out the right-hand side is the storage. So we have E dot in double prime minus E dot out double prime equal E dot storage double prime. 200 minus 182 equal 18 watts per square meter equal E dot double prime storage. So there are the three ways, or the three answers of what we're asked to find. Did we use anything from chapter 2 to solve that? No. Where'd it come from? It's all chapter 1 stuff. Then why is it in chapter 2? Well, you can solve it another way if you want to. All right. Let's solve it the other way. Go to the heat equation, heat diffusion equation. All right, one-dimensional, constant properties, no generation. This is what you get. Okay. Rho is in our kilograms per cubic meters. CP is our joules per kilogram. K, temperature. Temperature in degrees K. Time in seconds. Cancel, 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 cancel. This is joule per second, watt, watts per cubic meter. This is E dot double prime storage, because the air is going out of there. But I want the answer in watts per square meter of surface area. So I'm going to multiply both sides by V over A. V is the volume. volume is A times 0.3. A times 0.3. So this becomes 0.3. K told me, K is 1. Second derivative. First derivative. Second derivative. Okay. You can see what it is. Same answer. Same answer. By what method? Chapter 2, where's this problem? In Chapter 2, how does the solution manual work it? Chapter 1, I don't know why. Why would you do that? You're in Chapter 2 now. You don't do Chapter 1 stuff in Chapter 2. That's the whole point. So I'm just saying, you can work it either way. But sometimes don't believe the solutions manual, because you should work at Chapter 2 way. Yeah.
How would you then find...
Fourier's law, Chapter 1.
Okay, yeah.
you got to do it. There's no way around that one.
Yeah.
Yeah, right, exactly. Okay. Okay. All right, we're going to work one more example out of Chapter 2 at the start of next time. I think we'll stop for a day so I can do it all at one time, not break it up into 2 pieces. So we'll see you then. Homework was passed around. If you missed it, they're up here in front. And homework is due today. So we'll see you on Monday.